Okay, friends, so we are firmly entrenched into Unit 4, which is a look at the definite integral and antiderivatives in general. Two are somewhat synonymous, though not exactly. You'll notice that this is lesson 3. There was no lesson 2. I have combined lessons 1, 2, and 3 into 2 video lessons so that we can get everything done before Thanksgiving. That's the idea. So on today's show, we sort of make the jump and we connect this idea to this idea by the time we're done. And then we spend the next 3 lessons codifying that in something called the fundamental theorem of calculus. So, really? Let's dive in. On today's show, want to look through some properties of the definite integral. And the definite integral was that thing that we had started playing around with yesterday in our lesson time. And we had started playing around with it looking at areas under curves and saying, how can I get the area under a curve as a definite integral? So some things to consider. First things first. What if we take an integral of a constant function? Well, if we take an integral of a constant function, here's the function c, beep. I suppose that was b, but if this was c, between x equals a and x equals b, what is this area? Well, this area is the area of a rectangle, and that rectangle has length c and width b minus a. And so we would say that the integral of c dx from a to b is c times b minus a. So by way of example, if we were to do the integral from 2 to 6 of 8 dx, we would recognize that that's the area under a horizontal line of height 8 over a length of 4 on the horizontal. And so 8 times 4, 32. No calculus necessary. 8 times 4 is 32, and that's all you need. As a side note, if you wanted to use your machine, you can use your machine to do those integrals, because you have in the math menu of your calculator this beautiful thing called FNINT. And FNINT helps you find function integrals. I think that's what it stands for. So we take the integral of the function, then you have to tell the calculator 4 things. You have to tell the calculator what the function is. Then you have to tell it what the variable is, because it's from Texas and it doesn't know. And then where to start and where to stop. And your calculator tells you what that integral is. So the technology confirms what the calculus already told us, and we're good to go. As a side note, you should know how to evaluate integrals. You should know how to evaluate integrals on your machine. So if we were to take the integral from -1 to 2 of x cosine x dx, you should know that because we don't know how to do that yet, that is a finite problem. And I type x cosine x, comma x, comma -1, comma 2, and the calculator gives it to me. Yep, that's good. The calculator gives it to me. Because I'm in an AP course, I round to 3 decimal places, or I truncate. 0.020 would also be fine. Similarly, if I want to find the integral from 0 to 5 of e to the -x squared dx, Well, I ask my calculator what the function integral is of e to the negative x squared dx from 0 to 5, and the calculator tells me that I round to three decimal places or truncate either way. Now, because I have a calculator does not mean I should lose my brain. What if I'm looking for that integral and I want to find that without using a calculator? Well, then I think to myself, isn't that just that? Well, yes. So if I were to graph y equals x plus 1, except at that place where the hole is, I'm looking for that area, which happens to be the area of a trapezoid, where those are your dimensions, and so the area is 1/2 the height times the sum of the bases, and that's 4. Just because I have a calculator does not mean I should lose my brain. Am I okay? I'm okay. So we're still playing properties of the definite integral. I've got some more properties for you. Things to consider. The integral from a to b of f of x dx is equal to the opposite of the integral from b to a of f of x dx. This is one of those things that almost makes sense if you think about where the integral comes from. The integral is a set of areas of rectangles all added together. If you read those areas backwards, then all your delta x's go negative, and it turns your answer negative. So those are things to think about. If you read the interval backwards, then all the delta x's are backwards, and the integral is negated. The integral from a to a of f of x dx is 0. Well, consider some generic function on the interval from a to a. That's a very thin rectangle, friends. That's a very thin rectangle. The integral of k f of x dx is the same thing as k times the integral of f of x dx. In other words, constants can pass through an integral barrier like, some osmosis diffusion reference we'll throw in here. We've got to know those references. Why does that work? Well, in this case, we take a function, multiply it by k, add up all the areas. And in this case, we take the areas of all the rectangles and then multiply them by k. So in the case on the left, we're multiplying every rectangle's height by k, which in turn will multiply all the areas by k, which is what the thing on the right says to do in the first place. Of some importance, if you're adding or subtracting functions, well, that's the same as this. If you add the functions first and then take their areas, that's the same as if you add the areas individually. And that almost makes sense if we think about it. This guy also makes sense if we think about it. If you take the integral from a to c and the area from c to b, you get the integral from a to b. Picture time. some generic function, O, A, C, B, leprechaun area plus communist area equals total area. This almost makes sense. Of course, you're going to say, what if C is to the left? Touché. In this case, the integral from A to C is all this leprechaun area, but it's a negative integral value. Then the integral from C to B is all that communist area, but that's positive. So the leprechaun area that has a negative integral value adds up with communist area that's all positive in integral value, and we still get the integral from A to B of f of x dx. So there's still a cancellation that takes place. Okay, so what does that mean for you? Here's how it pops up. Let's pretend that the integral from 1 to 3 of h of x dx is 4, and the integral from 1 to 5 of h of x dx is, I don't know, 3. What if I want to find the integral of h of x dx from 3 to 5? Or I want to find the integral from 3 to 1 of h of x dx? Or I want to find the integral from, oh heck, how do I want to do this? From 3 to 5 of negative 2 h of x dx. How does that play out? Well, I have some function, h of x, and from 1 to 3, the area is 4. From 1 to 5, the area is only 3. The area, the net area, is 3, which means that in this interval, we've got to have a negative 1, don't we? Because the 4 plus the negative 1 has to add up to 3. And that means that the integral from 3 to 5 is negative 1. The other two questions are just properties of integrals we've talked about. If I read backwards, that negates my integral value. And if I multiply by negative 2 inside the function, inside the integral rather, that's the same as multiplying by negative 2 outside. Okay? Okay. A couple more things. One deals with the average value of a function. If f is integrable on AB, its average value on AB is 1 over b minus a times the integral from a to b of f of x dx. This is one of those things that makes sense more in picture form. So I've got some function, from A to B. Excuse me. I've got some integral from A to B. You've got to learn where the mute button is on that. And the area is that leprechaun area right there. That's the integral from A to B of f of x dx. The average value of that function, you have to imagine, is some horizontal line coming right through there, where if we could add up all of these y values and divide by infinity, we would get that red line. Well, if we were to take that rectangle, that's probably too low in fact, that rectangle should have the same area as the leprechaun area. That's what we want. And so what the average value thing does for us, what this thing does for us, is it takes our area that we desire, it turns it into some jello mold, and then we kind of cut that thing up and reorganize the pieces until we get the red rectangle, and then we just take the height of that rectangle, because this part's the area of the rectangle, and this means divide by the length of the interval. And if I do that, I get the height of the red rectangle, which is what I'm shooting for. I think we can do that. If I want the average value of a function on a closed interval, I take the integral and divide by the length of the interval. Well, that's easy to do. I've got a machine. Integral divided by length of interval. Not bad. Not bad. Hey, I've got 2 minutes, I think. Thing to think about. What is the connection that we're shooting for? I want to establish something that sets up our next 3 lessons. If you were to take the derivative with respect to x of a function that was itself an integral, the integral from some number a to x of some function, I maintain that that derivative is the same thing as our function evaluated at x. By the way, the t here is because the actual variable inside the integral is irrelevant. The integral is based on a function, not the variable we use inside. It's what we call a dummy variable. Not that you're a dummy if you use it, and not that it's a dummy. Well, basically it is. Never mind. So what do I mean by this blue function? Well, I mean that you have some function, some red function f of t. This is some red function f of t, and here is the value a. The blue function takes the area from a to x. It takes this area and plots it. So you can imagine out here somewhere at a, this blue function is 0. And then as we get further and further away from a, the blue function adds more and more and more area all the time. That's what we're imagining. And so what I'm looking to establish is that the derivative of the blue function is the red one. The derivative of the blue function is the red one. So what I'd like to do is I'd like to take a look at some function called capital F of x. And that's just the integral from a to x of f of t dt. And this thing is an area function. It is an area function. So if we were to look at the derivative of capital F with respect to x, it would be a limit as the change in x gets so small of the change in capital F over the change in x. Well, what is the change in capital F? The change in capital F is the change in a teeny tiny piece of area. It's literally the width of that green segment. It's the width of that guy. It's the economist's marginal cost. And so I think that it's pretty clear that the derivative of the blue function very much depends on the red graph. And if you can picture that area function in your mind, and you can connect the dots that the derivative of the blue function depends on the red, then the next 3 lessons are easy peasy. And I sure hope they go that way. Awesome. We'll see you tomorrow.